The first one is top lesson: no mission, no program. Never build a system hoping demand would appear. So build it, and they will come. It hasn't happened before. I don't see why we should think it will happen in the future.
Hello, welcome to the Space Policy Show. I'm Colleen Stover with the Center for Space Policy and Strategy at the Aerospace Corporation. Today's show is part of our series I've dubbed Going Faster. We've talked about faster intelligence, leveraging commercial companies. We've talked about faster launch to meet demand for responsiveness. But today's show is about literally going faster, like warp speed faster. Well, not quite. But we are talking about nuclear technology to power activities in space on the Moon or Mars, as well as nuclear propulsion to get us further faster. We are hosting Dr. Brian Weeden of the Center for Space Policy and Strategy and Dr. Bhavya Lal, former Associate Administrator at NASA's Office of Technology, Policy, and Strategy. The Space Policy Show has over 150 episodes spanning 5 years of space policy making, and you can check those out and the Center's research papers at csps.aerospace.org. All of our shows are on YouTube or podcast. Now over to Drs. Weeden and Lal to talk nuclear.
Thank you, Colleen. And Bhavya, thank you for joining us today to talk about this really important topic.
I'm thrilled to be here, Brian. Great seeing you.
To get us started, can you give an initial explainer on what we mean by nuclear power and propulsion?
Okay, so let's take power and propulsion separately. Within power, there's two primary types. We have radioisotope power systems, or RPS. Think of these as hot rocks that power your gear. They produce heat from a radioactive source called plutonium-238, which decays naturally and releases the heat, which is converted into electricity. No moving parts, no switches, just continuous passive power for decades. Output is very small, but it's reliable. And RPS has powered all of our space probes for the last 50 years, Voyager, Curiosity, Perseverance, and soon to go the Dragonfly mission. Now, we have fission reactors, which are basically familiar to us. These are miniature versions of Earth-based nuclear power plants. They split uranium atoms, control reaction, generate heat, which can be used for power or propulsion, and we'll return to propulsion. The big difference between fission reactors and RPS is that, unlike RPS, fission reactors can be turned on, they can be throttled, they can be shut down, sort of a volume knob. They're not new. The United States flew a reactor, SNAP-10A, in 1965, which operated for a month or so. Now we have nuclear propulsion. Nuclear propulsion has two main flavors as well. NTP, nuclear thermal propulsion, is like a chemical rocket on steroids. Instead of burning fuel, an NTP engine uses a reactor to heat a lightweight propellant like hydrogen, which is expelled to generate thrust. The key is that this decouples energy sources from the exhaust chemistry, allowing different kinds of propellants. And of course, we love hydrogen because it has the lowest molecular weight, which means the fastest exit velocity, which means, all else being equal, the best specific impulse, which ends up being twice as much as the best chemical rockets, which means faster trips to Mars, less fuel needed, which translates into lower launch mass and cost. It means shorter crew exposure to space radiation. For DoD, it means maneuverable spacecraft, which is critical in contested environment. So that's NTP. Then we have NEP. Here, just think electric spaceship. Basically, it's a fission reactor like the one we just talked about, but you bolt on ion or Hall effect or other kinds of thrusters. NEP gives massive amounts of specific impulse, but the thrust is low. It's great for deep space cargo, although it's not good for quick maneuvers. The way I think about it is, if NTP is a Porsche, NEP is the Prius, slow acceleration, ultra efficient, long range.
And can you unpack a little bit more about how these nuclear power propulsion technology you talked about are different or give different advantages than the chemical thrust and the cylindrical power that we've traditionally used for spaceflight?
Yeah, so think about nuclear. So a kilogram of uranium-235 fully fissioned has 3 million times the energy of a kilogram of coal. That's like replacing a freight train of coal with a softball-sized chunk of uranium. It's just, it blows your mind. And again, comparing, not just coal. So let's talk about solar panels. Solar panels are great near Earth, but they struggle past Mars or during lunar nights or dust storms on Mars. You would need acres of panels and tons of batteries to survive a 2-week lunar night. A fission reactor the size of a garden shed can do the job instead. Batteries, they run out after days. Reactors can run for years. Chemical rockets have high thrust, but they have low efficiency. I mean, there's only so much propellant you can carry with you. Obviously, there's propellant on NTP and NEP systems as well, but as I said, the energy density of nuclear is just so much higher. You get so much more for your, so much bang for the buck. The bottom line is solar lets you visit, nuclear lets you stay and build.
So as we're thinking about these technologies, what strikes me is that, when we were thinking about spaceflight as going around Earth orbit or sticking in sort of the inner solar system, as you described it, traditional chemical propellant thrusters and solar electric power was sufficient. But as we're thinking about going out further and also looking to stay or longer duration, that sounds like really where these new nuclear power pulse technologies are sort of the key to things.
That's absolutely correct.
So, you mentioned that the United States flew Operation Nuclear Reactor in 1965. What happened? We did a lot of investment back at that time period, but we don't seem to be doing anything since. Did we run into technological roadblock? Was it a shift in policy direction? Was there a lack of need? Can you talk about why we sort of went away from this technology?
So the short answer is it wasn't the reason we haven't flown a reactor since 65. It's not because we couldn't, but because we never stuck with it. So that's a short answer. The long answer is a little bit more complicated. In a way, we've been stuck in a doom loop. We have, we put out these big dreams, but there's no mission pull. Nobody is saying, NASA Exploration Systems Director is not saying, hey, space technologists, give us a reactor with an ISP of X, or give us a power plant, with a power level of Y, right? So there hasn't been a mission pull, although that's changing. So don't let me forget to return to that. And we've had unrealistic expectations, and then it's followed by cuts, collapse, and another reboot. So the Snap 10A, there was no follow-up because there was no committed mission or customers. So basically, most post Snap 10A programs became tech demos in search of a reason to exist. We kept searching for the perfect system, 200 kilowatts on the first day, instead of fielding good enough systems to learn from and scale. We've had leadership.
Sorry, Snap 10A, can you explain a little what that was?
Yes, Snap 10A was the first reactor we flew back in 1965. Sorry, good point. It operated for about 43 days. It was shut down, and that had nothing to do with the nuclear side. There was some voltage regulator issues. It is still out there. It may have broken up a bit, but it's still circling. Moving on to some of the other issues, we've had, we have a very fragmented nuclear enterprise. NASA often leads integration, DOE often builds the cores, DOD has funded pieces, but no one owns the full life cycle. Another really important concern is that there's a timeline mismatch. The way we've done things traditionally, technology takes 10 to 20 years to mature. But program managers in Congress and the White House priorities shift every 2 to 5 years. DoD palm cycles are, short cycles. So anything that's outside of those cycles doesn't really get attention. We have some issues around regulations as well. We still lack a streamlined, time-bound path to licensing and launching a reactor with clear interagency roles. Last but not least, we absolutely have an inadequate infrastructure. We don't have enough opportunities for enrichment. We don't have test beds. We don't have nuclear qualified launch prep facilities. Bottom line, we didn't fail because of physics. We failed because no one had the mandate or the staying power to finish the job.
It's interesting hearing you talk about the reasons why we didn't do that. The more I look into this, there's a lot of interesting stuff that we did in space technology in the late 50s and early 60s, thinking about things like hypersonics or other things that we sort of stopped investing in or stopped focusing on. And I think part of the question is, or part of the story there is what you mentioned, is that there was either a shift in direction or there wasn't a clear need or a clear pull to continue those investments. It almost seems to me like, absent that broader direction, what we had was good enough, what the mission we were doing, which again was a lot of kind of Earth orbit focus. Is that your sense as well?
I think with nuclear, there has always been this nice to have attitude rather than a must have attitude. And I think we haven't really sharpened that answer. So for example, if we really lay out the rules around, we want to live and work permanently on Mars, or we want to explore or the moon, we want to explore Europa or Titan, or we want to have around the clock lunar outpost, or we want to operate high powered national security assets in deep space. That in those scenarios, nuclear isn't just helpful, it is actually enabling. It's the only thing that works at scale. So, just to unpack that a bit. So what are some must-have use cases? Let's take lunar night survival. The moon has 14 days, 14-day nights, often in permanently shadowed craters. There's a lot of important stuff in permanently shadowed craters. For example, water ice. A surface reactor can actually power and warm habitats and allow you, for example, to mine this water, to conduct what's called ISRU, in situ resource utilization. For the outer solar system, beyond Jupiter, sunlight drops off fast. You are basically operating in a powered desert. RPS systems or reactors are the only viable source for any kind of mobility instruments and data return. Mars surface operations. So, as we hear a lot, SpaceX wants to go to Mars with chemical systems. Well, in order to make that return trip, you need to produce propellant on the surface of Mars. Well, you're not going to be able to do it with solar power, with the dust storms and all. You wouldn't, and in any case, given the low flux, you may need tens of football-sized fields of panels. And of course, now we also have, repair and all of that. So producing methane and oxygen for return trips requires continuous megawatt scale power. National security missions, maneuver without regret, or, dynamic space operations, as we call it today. If you want a spacecraft to change orbit unpredictably or loiter far from Earth, only nuclear can provide that thrust. So those are kind of must-have applications. But oftentimes we're thinking of these nice to have applications, so for example, short duration lunar missions. Solar and batteries may be good enough for brief crew visits or uncrewed landers, although obviously they also come with some constraints on location, timing, and mass. So I think the question isn't, is nuclear always necessary, but when does nuclear unlock a mission? As I said earlier, if solar lets you visit, nuclear lets you build. If chemical rockets can get you there, nuclear gets you back faster, safer, and with more payload. So it depends. For the boldest missions, the ones that aim to settle, defend, and industrialize space, fission isn't a luxury. But for others, it is.
Yeah, that's interesting. And your comment about the lunar night, right? We've seen some of that with the recent commercial landers that have attempted to go to the moon. Several of them have been limited by their ability to generate enough power and store that before the lunar night hits. And that's a real consideration for things that you just mentioned that are running off of solar electric and batteries. So it sounds like as the U.S. and other countries get more serious about long duration sustained presence on the moon, making the journey to Mars, establishing a presence there, that's really when nuclear becomes more of, I would compare it maybe as a necessary thing, as you put it, rather than just a nice to have.
That's exactly right.
Yeah. So, we've been talking a lot about the U.S. Obviously, the U.S. is not the only country that's looking at these things. Historically, the Russians have had a lot of investment, as I understand, they've flown a lot more nuclear power sources in space. Can you talk about why that was the case, and maybe a little bit what their experience was?
Yeah, so you are exactly correct, Brian. Russia has launched over 30 reactors that we know of for their Rorschach satellites during the Cold War. And you bring up this really excellent point, and actually it also reinforces something I said earlier, that for us, it may have been a luxury to launch reactors for national security purposes because our solar cells were very good. We were very good at GNC. We were very good at some things that we needed to be good at to watch what was happening on Earth. And in any case, the Soviets at the time didn't have the kind of global fleet that we needed to watch as carefully. But for the Soviets, that was actually an important thing. They did not have the kind of radar technology we did. So they had no choice but to launch reactors to be able to follow our, to track US carriers via radar, which means they had to fly kilowatt class systems in low orbit. Solar couldn't do it, nuclear could, so they did. So they had an actual need, which is something that we hadn't had in the past. So that's just, Soviet Union / Russia. China is making a lot of efforts too. They're planning and again, it's always hard to tell, but best we know, they're planning a 1.5 megawatt class reactor to power their lunar base by 2036. They're moving fast, possibly with Russian collaboration. In the meantime, we have spent, we actually don't know how much money on nuclear since the 1950s. And again,
we don't know how much money the United States has spent on this since the 1950s.
Yeah, there have been some estimates, but there's sort of no agreement. Best I can tell, we've spent about $20 billion over the last 60 years with one light bulb sized RPS to show for it. That is all we got. I recommend a GEO study on it. GEO, are you listening? You need to figure out how much money we've spent and what we got out of it. And again, I think it's a crying shame that we haven't made the same accomplishments others have with less money. And
my understanding also, the Russians, they eventually did shift away from launching nuclear reactors to power their spacecraft. Is that because their power techniques and solar power energy and radar techniques got better, or did they still continue using reactors to today?
So I'm not an expert in this area, Brian, but the best I can tell based on unclassified sources is that they did stop in the late 80s, probably because their solar and radar technology got better, and probably because they couldn't afford it. And they also have had at least one fragmentation event over Canada once, so I was probably sobering for them.
Yeah, and that was the Cosmos satellite that part of it which re-entered over Canada and created a radiological hazard which Canada had to clean up and then bill the Soviet Union for some of that cost. And it's interesting. It's one of the only cases where the liability convention, which is sort of the treaty dealing with some of that, has been mentioned, although it actually, as far as I understand, the Russians paid without actually invoking a full-on convention and commission. But it's an important point, right? Because it gets to the question of, some of the reasons why countries may not have always done this in the past is one of those questions of how do you deal with the safety and protecting the earth from some of those hazards.
Yeah, I mean, I think the Soviets were operating the reactor too low. I mean, the way the United States has conceptualized our reactors, we are not going to be turning them on until they are very, very far deep into space and they cannot fall back down. So yeah, so I think it was unsafe operation on part of the Soviets, which we don't plan to do.
And as you mentioned, we're thinking primarily not for Earth orbiting uses, but for the missions that are going out to cislunar space. They're going out to Martian space. They're going elsewhere in the deep solar system.
So for NASA, that is absolutely the case. NASA is looking at the moon, cislunar space, Mars, beyond. I don't think DoD has a firm plan yet, but DoD is bound by the same laws. National Security Presidential Memorandum 20 lays out the rules for how we launch space nuclear systems, and they apply to everyone.
So you mentioned apply to everyone, and you mentioned the government stuff. Is this something that commercial industry is looking at as well? So it's not just the government looking at this?
Yeah, so for me, that is the most exciting part. In recent years, we've had several companies that have come up that are actually looking at both terrestrial and space-based reactors. As I said at the start, I mean, there are some key differences. Obviously, space-based reactors have to be light, they have to be designed differently. For shedding heat, on Earth, you can shed heat by just convection. In space, there is only radiation, so you need to have radiators, which can get very big if the reactors aren't operating at high temperatures. So there are some differences, but there's also a lot of similarities. For sure, the industrial base, the supply chain, there's lots of the workforce, a lot of commonalities. So yeah, so it's very exciting for me to see commercial companies in this arena. And again, maybe if you have time, we can talk about why I think that may be relevant.
Yeah, I guess I shouldn't be surprised given all the various things commercial companies are involved in these days, but it does seem a little bit interesting that there's commercial companies working on nuclear reactors, and there is also the government, U.S. government has put in place the beginnings of a policy regulatory framework that would enable that, right?
Yeah. Right. I was going to interject and say we shouldn't be that surprised, though. The entire terrestrial nuclear enterprise is commercial, from mining to enrichment to deconversion to operating reactors. It is commercial, right? I mean, obviously, it got a start in government, right? The Manhattan Project. We did all these experiments to understand how you get energy out of the nucleus, but then the government built shipping port. Which was, I think, a reactor in Pennsylvania. And then from that point on, the commercial industry took off. And I think if we think about our space enterprise, our space nuclear enterprise correctly, we should be thinking about this from the start, that we would like power generation, at least power generation, if not power and propulsion, to be commercially owned and operated, and the government should be a customer, right? I mean, the government should just buy power on the moon like the government buys power on Earth.
Yeah, no, I still agree. I just think, again, most of the historical use of this, as you mentioned, were government missions. You mentioned Voyager and the Galileo probes and others, right, that using this. So I totally agree with you. And it should not be surprising given what's happened, as you mentioned, outside of the space sector. But it is a little bit new for the space sector itself to think about or have to, envision a framework where it is commercial companies leading this.
Yeah, and there's actually not just on the supply side, and there's plenty of companies, but on the demand side as well. There's companies that would like to purchase power on the surface of the moon and do their ISRU operations or other activities. So there's both a commercial supply and a commercial mission pull. And certainly, there is at least one company we know that would like to have nuclear power on the surface of Mars.
So as we look to kind of what comes next, you mentioned there's two major different categories of nuclear propulsion: the nuclear electric propulsion, nuclear thermal propulsion. Based on your research, do you have a sense whether one of those maybe should get a higher priority than the other, or is it unclear at this point?
So first off, I think it's a false choice. This isn't a binary decision. It's not Coke versus Pepsi. It's more like entree versus dessert. It must be lunchtime. I'm using food references. So we want both. But I think the question is, I think we need to think about the order, the portions, and what our stomach, read budget, can handle. So here's an analogy I used earlier, Porsche versus Prius. One is built for speed, the other is built for efficiency. You wouldn't take a Prius to a racetrack, and you wouldn't rely on a Porsche to haul your belongings cross country without stops. We just moved from Santa Monica to DC. Same here. NTP gets crew to Mars quickly, and EP moves cargo efficiently over distances. Different tools, different missions. It is not either or, it is mission match. So we need both. So, you mentioned the study that we just did. And this is what we found. Our finding was that, yes, we need both NEP and NTP. However, what we need first is power, because nothing flies without that reactor. Fission power systems, tens to hundreds to eventually thousands of kilowatts are the base layer. Every future surface mission or NEP mission builds on that. NEP is basically powered with thrusters bolted on. So once the reactor is flying, you're most of the way there. Even NTP, while it uses different physics, which I described at the start, still needs shared enablers, autonomous controls, high temperature materials, radiation hardened sensors, launch protocols. So how do we start? You start by flying a surface or an in-space reactor, prove that we can build, integrate, license, launch, and operate a nuclear reactor in space. NEP becomes a natural follow-on. Once power is fielded, NEP timelines compress dramatically. NTP actually can proceed in parallel if DoD brings a mission and a budget. If not, it risks the same pattern we have repeated before: a grand vision, no execution. So I would say let's stop arguing NEP versus NTP. We'll need both. But if we don't start with power, we'll get neither. So in my mind, the sequence is clear: power, NEP, full ecosystem.
It's a really interesting path, and I think it's a great way to think about sort of the advantages of both systems, but also I think it's a great point about sort of the timing and the sequencing of these things. And of course, you start with power. Power is pretty darn important. We also talked previously about some of the reasons why the early efforts that the United States had in this area did not succeed. Are there any other lessons from your research for policymakers on kind of maybe how to avoid some of the challenges that we ran into in the past and turn this into the sustained effort that you have argued that we need to have?
Yeah, so some of this I'll be a broken record, but maybe there's some new ideas too. So the first one is top lesson: no mission, no program. Never build a system hoping demand would appear. So build it and they will come. It hasn't happened before. I don't see why we should think it will happen in the future. Let's start with the user, a use case, and a deadline, and we have enough cautionary tales. The second one is avoid the perfection trap. I think we always want the moonshot, but even the moonshot began with the Gemini program, right? So, or was it the Mercury program? Somebody will correct
Mercury,
me.
then Gemini, and then Apollo.
Mercury, right? Yeah, Mercury. So you need to start with a minimum viable product, and then build something small, fast, and real, and then improve. The third one is, give somebody the keys. One office, real authority, real budget, no diffusion. The Manhattan Project had Leslie Groves. Naval Reactors had Admiral Rickover. You need a nucleus, nerd joke, of accountability. Fourth, I think we do need to plan for political cycles. We need to break programs into fundable, testable milestones. So, for example, let's say we are going to do a power demo. let's set a 2028 ground test, if not a flight test, and then celebrate those wins. Avoid 10-year timelines with no payoff till year 9. Fifth one is, we do have a regulatory mess. We need to fix it. We need to create a clear space-specific nuclear launch approval pathway with deadlines. Policymakers, we need to invest in people and places. Right now we don't have enough qualified engineers. We don't have hot cells. We don't have test beds. None of that will lead to a reactor. We need, every time we start a new cycle, we rebuild infrastructure and then we let it waste away. Some new ideas I've had is, let's fund multiple paths. There's a lot of infighting going on in the nuclear community on whether we use highly enriched uranium or low enriched uranium, whether we use for power conversion Stirling cycles or Braden cycles. Let's find fun, if we are especially, connecting back with the previous point we were discussing, if we are taking a commercial route, maybe a public-private partnership, let's fund multiple entities, like Operation Warp Speed. It used to take us 10 years to create a vaccine. Operation Warp Speed, we did it in 10 months. And there's lots of reasons, but one of them is for sure, they bet on multiple designs, not just the prettiest PowerPoint. So let competition and performance guide this down select.
And to give another space example of that, right? The Commercial Cargo and Crew Program, right? Where they saw multiple commercial competitors, and at the end, they had different designs, different approaches that, are now being used to service the International Space Station.
Exactly. And last but not least, I think we should fear delay more than failure. A good enough demo in 2028 beats a perfect one in 2040 that never flies. Speed builds credibility and fielding builds momentum. So those are my lessons for policymakers.
Well, that's what I think you've laid out some really interesting ideas and a really great roadmap for how the United States can get back on the track of developing these technologies, which we've talked about are really important for the long-term, big picture goals we're trying to get in the space community. What do you think is the biggest misconception about space nuclear power propulsion you wish you could dispel?
So the top myth, it's too dangerous. People hear nuclear and picture mushroom clouds. But space nuclear systems aren't bombs. They're little miniature, rigorously engineered machines with multiple layers of containment and passive safety. Here's what is often misunderstood, and we need to better narrate it. Space reactors are actually intended to be launched cold. They don't turn on until well after reaching orbit. And if there's a launch failure, there's no chain reaction, there's no meltdown, there's no fallout. Radioisotope systems, RTGs as they're often called, have flown safely since the 1960s. In fact, there was an RPS on Apollo 13, which, as you know, survived a fiery re-entry. The RTG survived that fiery re-entry and now rests intact on the ocean floor. No leaks, no hazard. Radiation exposure is low, despite what people might think. Standing next to an NTP engine for a year on Earth gives you less radiation than a dental X-ray. Meanwhile, cosmic rays on Mars are hundreds of times worse. So safety is not a showstopper. In fact, as I mentioned earlier, we did fly a reactor in 1965, and the Soviets have flown over 30. The technology works. It has been demonstrated. So that's the biggest myth. The second big myth is there is a sense, which is kind of almost the opposite, that we are basically ready and it's all about cutting the red tape. That's also wrong. While we've made huge strides, we are not there. Here's the reality. We've spent decades stuck in R&D with no flight since 65. Most systems lack qualified fuel, launch-ready designs, and of course, regulatory approvals. Programs die not from lack of science, but from missing mission pull, fractured leadership, and unstable budgets. It is execution, not engineering, that's a bottleneck. So myth 1, it's too dangerous, false. Myth 2, we are ready to fly, also false.
Any last things you want to share with us today?
Yeah, I guess I would say the bottom line that if we want a future in space powered by space nuclear power, as I think a lot of us agree we do, we don't need to reinvent the wheel. A lot of the pieces are already in place. We just need to stop driving in circles, pick a path, begin, and just not stop till we are done. These starts and stops are what's getting us each time, and that has got to stop.
Well, it's been really great talking to you with us today. Thank you. Thank you, Bhavya. Really appreciate it. And now I'll turn things back over to Colleen.
Thank you, Brian. It's been awesome talking to you as well.
Well, thank you, Brian and Bhavya. Indeed, space nuclear systems are not bombs. That's a great quote. And the comparison between traditional systems like combustion, propulsion, or solar power is definitely valuable. To our audience, thank you for joining. All of our shows are available on YouTube or by podcast. You can subscribe or follow us to get notified, engage with our speakers on LinkedIn, and check out other shows in our 6-part series, Going Faster, as well as our deep research papers at csps.aerospace.org. Thank you to James Liggins, our technical director. Until next time.